I didn't put the numbers on the board this morning because I'm expecting that most of the questions we had for this session are pretty straightforward. I don't want to, now it sounds kind of bad for me to go, but were there any areas of particular difficulty? Are there questions that you would like to go over, make sure that we go over? Because we'll probably have time to do them all. Yes, sir? 6? Number 11? Yes, ma'am? 3? Any others? So number 2 has to do with valence electrons in a configuration. 3 has to do, let's see. Oh, carbon silicon. Okay. 6, fundamental differences, and 11. Okay. Oh, so for those who have something to turn in, they're in, correct? All right, let's start with answers from the floor then. There's enough chatter. I'm sure there's people looking for opportunities to talk in an appropriate way, so let's do that by answering a few of these questions. Number 1, what are valence electrons and why are they so important in chemistry? Yes, ma'am. Right. So you got most of the elements of the book answer for that. So correct. Valence electrons are the electrons that are the farthest away from the nucleus of an atom, and they're important. So they're farthest away. That's the significance, and they're also significant because of the characteristics they give. It says here that they're important because they are responsible for determining the chemical behavior of an atom. So those valence electrons on the outside are basically those things that control the chemical behavior or the chemistry that element will get involved in. Which things it will mix with and how many it takes to mix with so many of another. That's all based upon the valence electrons, how many they have. That also is kind of connected to the other question about silicon and carbon. The next question, or question number 3, it says, the chemistry of life is based on carbon. And this means that all of the molecules which govern life-giving chemistry have carbon atoms as their principal component. Now, carbon, we mentioned before, how many connection points does a carbon atom have on it when it's looking for electrons? Right. It has 4. Carbon has 4. And it's right in the middle there. It's trying to connect with, not to get rid of. It's looking for more, and it's looking for 4. So whenever you combine something with it, like CH4, you get very symmetric molecules. But it's got 4 connection points at which it can connect to other things. As a matter of fact, it can connect with, so many different things with those 4 connection points. But we said that the chemistry of the carbon is primarily determined by its valence electrons, how many valence electrons it has. So looking over here at carbon and silicon, these two, they're both column 4A nonmetals. So they're both looking to receive. And how do carbon and silicon compare when it comes to valence electrons? They have the same number of valence electrons. They're both in column 4A. They both have 4, and they're both looking for 4. And so that's why in this question it talks about speculation about silicon-based life, because you could, in terms of the chemistry, replace a carbon with a silicon and have the same exact structures. Whatever a carbon would do in there, a silicon would do in there as well. It's just that we have so much carbon compared to silicon. The book answer on 3 says, since life is based on carbon, it could in theory be based on any atom in the same column which will have a similar chemistry. It could in theory be based on any, in life as we know it. Now, some people argue, we argue for carbon-based life form. There may be other life forms based on something other than a column 4A type element. But in terms of life as we know it, silicon would still be very different from carbon-based. but the chemistry would look very, very, very similar because silicon and carbon both have 4 valence electrons. Their chemistries are incredibly alike. All right? So does that answer 2 and 3? Or excuse me, answers 1 and 3. Was that your question, Blake? Number 3? So does that... Who asked on 3? Was that sufficient answer? Okay. Number 2 asks, how many valence electrons are in the following electron configuration? And basically counts up to the 5p3. So let's go ahead and write that out, going up to 5p3. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, okay, 5s2, 4d10, 5p, was it 3? Okay. So there's the whole electron configuration, and just if you do watch these videos, the black doesn't show up on the white very much, so most of what you're going to hear is me talking. You're not going to see these very well. So if we were to produce these videos, we'd actually replace the whiteboard with, so you could see it, put something in there digitally. But us doing it live here, we can hopefully see all the way across here. And the question says, how many valence electrons are in this configuration? So what am I going to look for first? The first step in figuring out the valence. Highest energy level. Where's the highest energy level? Where's the energy level indicated? Pardon? The coefficients. Okay. The coefficients. So as we count them up, looking for the highest coefficient, looking across from left to right, we could go from right to left, obviously, but looking for the highest one here is a 5. And it occurs in 2 places, the 5s2 and the 5p orbitals. The question was how many electrons, how many valence electrons? So what we do then, once we've identified the coefficient that's the highest, then we look at the superscripts above those orbitals. So we have 5s2, which gives us 2, and a 5p3, and 2 plus 3 is equal to 5. We also then, knowing this, 5p3 would be 1, 2, 3, 4, 5, sp1, 2, 3. What column is that element in? 1, 2, 3, 4, 5. It's a column 5a element. So we would expect to find 5 electrons in the valence. So you could do it both those ways, counting up, looking at the highest energy level and then counting the superscripts, to the sum being 5, or identifying it as being at the 5p3, finding the element and realizing that it is in a column 5a. I'll write it as a Arabic rather than Roman, a 5a element, meaning it's going to have 5 electrons in the valence shell. Any questions on how I did that both ways? One from the electron configuration and one from the periodic table. If not, then we're on to answers 2. The person who asked 2. Anybody? Nobody did? Okay. Number 4, what are the noble gases and why are they important? Where are they located at, the noble? The far right column, the 8A column, correct. So this whole column here represents the noble gases. And why are noble gases so significant? Right, they don't want to react, and that's true. They don't want to react. Why don't they want to react? Right, they have the ideal configuration. They have the complete octet full. And they fulfill the octet. Remember, helium up there is an exception. It doesn't want 8, it wants 2. But other than that, every other element has a complete p shell full. So since they all have 8, they're noble, they're inert, they don't want to react with anybody. They're completely satisfied where they're at. Question 5 asks, what is the octet rule? And give 2 exceptions. We just said it. What is the octet rule? The octet rule, the ideal configuration. Okay, and what is that ideal configuration? 8 valence electrons with 4 exceptions. And these 4 still fulfill what we call the octet rule, but they're not looking for 8. They're only looking for 2. And those would be hydrogen, helium, lithium, and beryllium. Okay? Hydrogen is going to go to 2 by gaining 1 and becoming a 1s2. Lithium is going to become 2 by losing 1 and become a full 1s2. Beryllium is going to want to lose 2 and fall back to a 1s2. Then we get up to boron. Boron's flaky, remember, and then carbon starts adding from there on up. So if it says, what is the octet rule? The octet rule is that elements want to have a complete valence shell of 8 electrons, with the exceptions of those 4 elements which want 2. And even though they only want 2, we say that they are satisfying the octet rule, because the octet rule has within it those 4 exceptions. Okay? Any questions on that? Like I said yesterday, these are mostly concepts. There's no computation here. It's just understanding. Number 6 was one of the ones that was specifically asked, what is the fundamental difference between metals and nonmetals? Someone else. You get another turn in a minute, Jess. Fundamental difference between a metal and a nonmetal. Right. Go ahead and put the jagged line up here or highlight that for us one more time. And when we figure out the characteristics of the elements, which also then tell us what kind of molecules they're going to form, the difference between a metal and a nonmetal, the primary difference is that metals want to lose electrons. And in losing electrons, those metals, we can pick something over here, potassium, let's say. Potassium has 1 valence electron, right? The 1s, or the 1, 2, 3, 4, 4s1 electron is its valence electron, 1. It wants to get rid of that 1 so it can fall back to the full configuration of argon. It wants to fill the octet by losing 1. And when potassium loses a negative, losing a negative makes it more positive. Metals want to become positive. They want to lose electrons and by doing so become positively charged. Nonmetals over here, for example chlorine, all the way over in column 7, is a nonmetal. Nonmetals want to receive electrons in order to fill the octet. And when they receive an electron, electrons are negative, they become more negative. So metals want to give electrons and therefore, and by virtue of that, become positive. Nonmetals want to receive an electron and by virtue of that become negative. Let's see what the book says. The metals tend to give up electrons to attain the ideal configuration. Nonmetals tend to gain electrons to attain the ideal configuration. And the person asked 6, is that sufficient answer? That's the book answer. Does that make sense? Okay. Number 7 asks, critique this answer. The number at the top of a column on the periodic table is the number of valence electrons that all elements have. Okay. We've been dealing with this statement primarily, but is this statement absolutely true? No, it's not absolutely true. Nuance it a little bit for me. The number at the top of the column, give a little more qualifier there. For the A columns, we called them, remember? this was 1A, 2A, 3A, all the way up to 8A. Those are the A columns. These columns in here are also referred to as 1 through 10B. And so to say that the number at the top indicates the valence shell is not absolutely true in all cases on the periodic table. It's only true for the A columns. Now, some other periodic tables aren't numbered 1A, 2A, 3A, 4A, whatever. Not. They go all the way across 1, 2, 3, 4, 5, 6, 7, from left to right. But using the A column indicators helps us here. If you look at this periodic table over here, this shows both kinds of indicators. Over here is column 1, and underneath it indicates 1A, and 2, 2A. Over here is 13 and 3A. Okay, the 3A, we've been focusing on these Roman numerals and then the A's. I've been writing them Arabic sometimes, but 3A, 4A, 5A. When you see the A following it, that's what we're using in terms of valence electrons. Over here, though, column 3B doesn't necessarily mean that it's looking to become an ion with a 3 charge differential. So look to the A columns to get that information. That's why right now for the scope of this course, when you're dealing with the metals that are in the middle here, these indicated as transition metals. The transition meaning there's something other than the standard, there's something else going on. That's where you're going to be using the exceptions with the Roman numerals 1, 2, 3, and 4 to indicate the kind of charge that that ion wants to take on. Because it's a little bit above the scope of this course right now to go through and explain why that is. We just accept it at this point. Number 8. What is the difference between an atom and an ion? Yes, sir.
An atom has a neutral charge and an ion has a positive or negative.
Okay. That an atom has a neutral charge or has no charge. Doesn't mean it doesn't have any charges. It has a net neutral charge. Whereas an ion has a charge. It's either positive or negative. And that positive or negative charge is created because there's an imbalance between the number of protons and the number of electrons. If there's more protons than electrons, it has a net positive charge. Positive by however many more protons there are than electrons. And if it has a net negative charge, it's because there are more electrons than there are protons. And again, the charge would be what the difference is. Elements, when we talk about the neutral atoms, we talk about, okay, for example, if we're looking at sodium again, it has a atomic number of 11. We say that that's because it has 11 protons in a nucleus. And the atom of sodium therefore has 11 electrons because there's one negative for every positive, so the atom has a net neutral charge. As soon as I add or take away electrons to the neutral atom, I have an ion. We talked about cations and anions, right? Cations and anions. And which one is positive and how do you remember it? How do you particularly remember it? Okay? No. So for Rebecca, what were you saying? Cat ions, did you kind of give how you remember which is which?
I hate cats,
So you don't like cats. So it's the opposite for you. So, you don't like it, so therefore cats is positive. Is that what you're thinking? Okay. For people that like cats, cats are, hey, you're positive. You're all in favor of cats. Okay? If you don't like cats, then you think, well, cats are negative, therefore it's the opposite. But you can get all confusing doing that. How many different ways do you want to try to remember something? If that works for you, fine. I just recommend that if you are a cat lover, that you remember that cats are positive, so cations are positive. If you're not a cat lover, that the A prefix means what? Negative or not in language. So, yes, ma'am?
or if you're a Kentucky fan.
Okay. I understand. So if you're a Kentucky fan, yeah, but if you're an Orange fan, it doesn't really apply. Anyway, so cations, if you like cats, that's positive. Anions, the prefix A means against or opposite or negation. And so I remember it this way. I'm not a cat person, therefore I remember that anions are negative. Okay, the A is a negative kind of a term. So maybe a question on the exam might look something like this. When a metal becomes an ion, which kind of ion does it become? A cation or an anion? Metals give away electrons, they become positive, it's a cation. Nonmetals want to receive electrons, they become more negative, they are the anions. Number 9, what is ionization energy? The ionization energy, I just abbreviated IE, but ionization energy. Do you remember? Yes, ma'am. Right, so it's energy needed to remove. The energy needed to remove an electron is the ionization energy. How much energy does it take to make an atom into an ion? Think of it that way, to produce the ionization effect. The energy needed to remove it is the ionization energy. Book answer, ionization energy is the amount of energy needed to take an electron away from an atom. The next question says, name 3 periodic properties of atoms. So we've already caught one on the board, right? Ionization energy. What's another name for ionization energy that I mentioned? Ionization potential. So ionization energy or ionization potential. That's one of those periodic properties. What's another periodic property we talked about? Electronegativity. So ionization energy or ionization potential is the energy needed to take an electron away to make an ion. What's the electronegativity? How much an atom seeks to gain an electron, how much it is willing to give to get that electron. See? So how much it takes to remove an electron and how much an atom is willing to give to get an electron. And the third periodic property we talked about? Atomic radius. And I just abbreviated that with a capital R. I know in most of your math formulas it's a lowercase r, but for in here I'm just using R for radius. So ionization energy or ionization potential, electronegativity, and atomic radius. Now what does it mean if something is a periodic property? What does the word periodic mean? A periodic property is something, right, where it is, it's something that repeats or something that has a trend. Okay? If something is periodic, it has a table, it has a trend to it. And a periodic table, showing here having a periodic property, means that we can look at the periodic table and see certain trendings. And we did that in class here. We compared these 3 periodic properties and we put them on the periodic table and said, as we look within a column or within a row, and we can say, I'll say absolutely we can say within a column and within a row, and more generally between 2 things that tend to be on a diagonal, but we may not be absolutely sure. What are the different trends? The trends for ionization energy, ionization potential, electronegativity, and atomic radius. Looking at a periodic table, I'm going to go ahead and draw the 2 diagonals. And I'm going to say that some of them increase as we go up and increase as we go right, and others increase as we go left and as we go down. So which of these periodic properties increase as we go up or as we go to the right? Excuse me? Yes, ma'am?
When it's convenient, could you please send Aaron Rice up here to
Yes, ma'am. Is it convenient, Aaron? Okay. This will probably be posted too, whatever you miss. You'll be able to see it, okay? So the periodic properties of ionization energy, let's stick with that one. Ionization energy, electronegativity, and atomic radius. And we said that the trends on these were that ionization energy and electronegativity increased as you went from bottom to top and as you went from left to right. That ionization energy and electronegativity trended in the same directions. In other words, if it took more energy to take an electron away, that same element is probably going to give more energy to get. In comparison, metals, they're not going to put up much of a fight to hold on to their electron, and they're not out there trolling to get another one. As opposed to columns 6 and 7, over here on the far right-hand side, they are desperately looking for another electron, and they're not going to give up what they already have. See, those are two ways of looking at the same thing. Ionization energy and electronegativity. Ionization energy, it's going to take a lot of energy to take one away from them. Electronegativity, they're not going to, they're out there looking, and if they find one, they're going to pull like crazy to get it. So there's, really, they're going to apply a lot of energy to fill the octet. And then the remaining one, the radius, we said was the opposite of that. The radius increases as you go from top to bottom and as you go from left to right. It's the opposite. If you remember in class when I was talking about how to remember this, one of the directions for the radius makes sense and the other one really is kind of counterintuitive, right? I mean, one of them, it makes sense that the atom is getting bigger and bigger. Its electron clouds are getting farther and farther away from the nucleus. And that trending is when we go from top to bottom. We're adding energy levels. First energy level, second, third, fourth, fifth, sixth, seventh. As we add more energy levels, it kind of makes sense that there are more and more electrons being built out from the nucleus. That to me is intuitive. It makes sense. This direction of radius makes sense. What doesn't seem to make sense is as I go from left to right, I continue to add electrons as well. But the nucleus doesn't get bigger as I add electrons. The radius doesn't get bigger as I add electrons. The radius actually gets smaller. So as you add more, it takes up less space. The electrons become more condensed. And remember, the reason for that is, though I'm adding an electron, I'm also adding a proton. And I'm adding it within the same energy level. And so the pull from the positive center to these individual outside electrons causes the radius to actually condense. They actually come in. So the trend is from top to bottom, it gets larger, and from right to left, the radius gets larger. And that was number 11. So, yes, sir. Yes, you may. The individual who asked about 11, I can't remember, but did that answer your question? Okay. Number 12 says, what's the fundamental difference between an ionic compound and a covalent compound? The fundamental difference. When it gets right down to it, what is the difference between covalents and ionics when it comes to molecules? I'm sorry? Yes, and unfortunately, please take your sweater off. Okay, metals and nonmetals, but because they're metals or nonmetals, it creates the fundamental difference, and the fundamental difference is, as Blake said, that for an ionic, you're transferring an electron. Okay? An ionic compound transfers, what happens is an element transfers an electron, becomes an ion. Another element receives that electron, and it becomes an ion. So we have a cation and an anion. Those two are oppositely charged, and then they're attracted to each other. So like magnets, they come together, and now we have a molecule. That's an ionic. A covalent, there is no electron transfer. There's no electron that ceases being an electron of sodium and becomes an electron of chloride. Okay? What happens in a covalent is the elements decide. They get together and have a vote. No, not really. But But they get together and the decision is to, rather than to take and receive, the decision is to share. And so one electron now has two different homes. It's split between two different places. You know, that electron is at sometimes around the nonmetal and at sometimes around the metal. But when it comes to filling the octet, this shared electron, or more accurately, this shared electron pair, whose octet does that pair belong to? Those two electrons. Who gets to count them as being part of their octet? The metal or the nonmetal? Correct, both. The electron pair that's being shared counts towards the octet of both elements. Okay? So that's the fundamental difference. When an electron goes from a metal, it leaves the metal and makes it into a cation and goes to the nonmetal and makes it an anion, that electron now belongs to the nonmetal to form the ionic bond due to charge differentials. But in a covalent bond, the electrons are never transferred. The ownership is never transferred. Electrons are now shared. And that sharing of an electron actually forms a stronger connection between those two than does transferring an electron and then just having opposite charges. Those covalent bonds are stronger than the ionic bonds. From the book, what's the fundamental difference between ionic compounds and covalent compounds? Ionic compounds form when atoms give and take electrons. Thus, they are composed of ions. Covalent compounds result when atoms share electrons and then no ions are formed. There are no ions in a covalent molecule in the way we've been talking about ionic molecules. They're not bound together because of charge differential. Number 13, what is wrong with the following formula? Mg2O2. Yes, ma'am.
It's not a stable molecule.
Yeah, right. Let's look at Mg. What is, if you looked at this and say, is this a metal or a nonmetal? Magnesium's a metal. Oxygen is a nonmetal. And I would expect then that we would have a covalent bond going on here. There'd be electron sharing. Magnesium, or excuse me, misspoke, didn't I? It's ionic. It's a metal and a nonmetal. I would expect an ionic bond to be formed here. But magnesium wants to take on what kind of a charge? +2. Right up here is a 2+. And oxygen wants to take on what kind of a charge? 2-. So we've got my cation and my anion of positive and -2. If we follow the rule that the shortcut that we learned in here, if we ignore the signs and transpose the superscripts as subscripts, we would come back and say, yeah, Mg2O2, and it would appear to be correct. However, what's the last step in the simplified? We have to go to the simplest ratio. It's Mg2O2, but the simpler ratio between these two subscripts, 2 to 2, simplifies to 1 to 1. And we end up with MgO. And you can see that if you know that each magnesium wants to become a +2, and each oxygen wants to become a -2, that when you bring two of them together, they neutralize charges. The +2 and the -2, you just need one of each to bring them together and have a net neutral charge. Okay? So you're not going to have Mg2O2 molecules, you're going to have MgO molecules. And rather than having one Mg2O2, you're going to end up with two MgOs. Don't worry about it. We'll get there soon. Just know that when you use the shortcut and get the subscripts, they have to go to the lowest common factor, okay, for each one of them. In this case, 2, they both reduce down to 1. Number 14. Let me read the book answer for 13 quickly. All ionic formulas need to be at the lowest possible ratio, so the equation must be MgO. Number 14. What gases are involved in Earth's 3-tiered protection system against high-energy light that comes from the sun? All right. Yes, ma'am.
Nitrogen, oxygen, and ozone.
nitrogen, oxygen, and ozone. Remember, we had a triple bonded nitrogen, we had a double bonded oxygen, and we had a double and single bonded ozone. Okay, now see if I get these right. We had certain rays that would come down and obliterate the triple bond. Remember what rays those were? Gammas, yeah. So gamma rays come down and they can break the triple bond. The next kind of ray that came down, it can't break a triple bond, so I'm just going to indicate that it couldn't break it by going through it. Technically doesn't go through it, but it has no effect on that. It breaks up the double bonds. Not yet. X's, yeah. X-rays, and then the last one, it doesn't break triples, it doesn't have enough energy to break doubles, but it can break singles, and that is the UV rays. Right? The UVs are the ones that give you sunburn. Okay. Whenever a gamma hits a triple bonded nitrogen, because this is a homonuclear diatomic, right? We're going to remember those. The homonuclear diatomics, hydrogen, then we're going to come across here the nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine. They all want to hang around as homonuclear diatomics, two of the same bonded together. And they form different kinds of bonds. Nitrogen forms a triple bond. And of these three rays, the gamma is the only one that has the strength to break the triple. Why? Because gammas turn Bruce Banner into the Hulk. They're strong. Okay? So gammas can break the triple. But when it breaks the triple, it takes a triple bonded nitrogen molecule, the gamma hits it, it destroys the triple bond, the gamma ray is completely used up, so the energy is gone, but now we've got two nitrogen atoms who then come to get back together and naturally reform a triple bond. And so that protection barrier is getting broken up and reformed continually, perpetually, all the time. The X-rays come through, they don't break up triples, but they have enough energy to break up the doubles. So the X-rays hit the double bonded oxygen, the same thing happens. The O2 molecule gets hit with the X-ray. That causes it to break apart and become two independent oxygen atoms. Those two independent oxygen atoms have used up all the energy from the X-rays, so the X-ray is no longer an issue. But then those two free oxygens naturally combine back together again because they're homonuclear diatomics, and they reform the O2 protection layer. And then ozone. Ozone exists, it's a good thing. We talk about ozone in the atmosphere. What we're actually talking about is a depletion of the ozone in the atmosphere. The concern being there's not enough ozone. And as the UVs come through, they don't have the energy for break up a triple, they don't have the energy to break up a double, but they do have enough energy to break up a single. And so the same thing, the UV gets used up in breaking up the single bond in the ozone. The ozone breaks apart, okay? But what you end up then with is an oxygen molecule and a single oxygen. And the tendency then is for the single oxygens to reform as oxygen molecules, not as ozone. And so the number of single bonds available to use up the UV rays is depleted. Several different natural processes, but they do. But it's at the rate at which they reform is the issue. Yes, ma'am.
Do they always come together in pairs?
Yes. Yes, it's always going to be two. You're not going to have an N3 molecule. You're not going to have an O3. I'm going to say naturally occurring. Not that you never would, but it's not stable. It's going to go to these. Okay. So, number 14, nitrogen, oxygen, and ozone protect the Earth from the harmful rays of the sun. And number 15 is the question about listing the homonuclear diatomics. And I'll just mark them on the board here. Just make sure we're all on the same page. We have this one, which is kind of out of place. But if you think in terms of metals and nonmetals, it would be over here, right? So hydrogen, and then it's nitrogen, oxygen, fluorine, and then add column 7, the unknown 117. Those are the homonuclear diatomics. 1, 2, 3, 4, 5. Yes, sir.
So we have to write the 117?
No. No, I'm not going to ask you that one. But even though we don't necessarily know what it is, we know that it's going to have that same property.
They know it's there, they don't know what it is. Or do they just assume it's there?
Some of these have been filled in, but they're synthetic. They're made in a laboratory, but they have lives that are so short that they exist just for milliseconds, just really small periods of time. So they do exist at times, but they cease to exist almost immediately. They're very unstable. These are very stable. These ones, you know, they sit around until they have a chemical reason to change.
So the ones with the white letters are the ones that don't last long?
I believe in this, these are showing the white letters as the ones that have been, these have also been synthetically produced. But remember, when they first came up with the periodic table, that many of the things we take for granted up here that are the stable, they didn't even know what they were yet. And when they put the periodic table together, they were able to say, I'm missing an element over here, but I know it has these qualities. I know it'll behave this way. Why? Because there are trends in the table, and I need it to fill a gap. And I know if I know the characteristics of the elements around it, I can predict how it's going to be. You know? And by using that predictions, they can then say, like, how do I know that these are going to bond in that way? Because they're all looking for an additional, these ones here, these are all going to form a single bond between themselves. Because they're all just looking for one more electron, so they're each going to share one. This is going to share 2, this is going to share 3.